Okay, so today we're going to do chi-squared of independence. Chi-squared test of independence. It's a hypothesis test. And so let's consider an example to give us context of what's going on here. So this gentleman carried out a study where he observed people on a path and they were handed a leaflet. The researchers varied the amount of trash or the litter in the area and observed whether if the person dropped the leaflet or not. When there was no litter, they observed 17 people that dropped the leaflet and 102 that did not. With 4 pieces of litter, they observed 28 who dropped it and 91 who did not. When there were 16 pieces, there was 48 people who dropped the leaflet and 17 who did not. And so what we're asked to find is, did litter in the area have a significant effect on one's likelihood of dropping the leaflet? And alpha is 0.01, and this chi-squared critical is 9.21, which we'll talk about a little bit later. So what we're going to do is we're going to define the test. The first thing we're going to do, we're going to name the test. We're going to do a chi-squared. That's what this is a Greek letter, chi. It's C-H-I, chi-squared test for independence. And we studied 2 chi-squared tests. We studied this one and one called goodness of fit. The next thing we're going to have to do is we're going to define the variables and make a table if necessary. So in this particular case, I'm going to make a table. And here's my table. And what the categories are, basically, is I am going to have a category. This is whether if they are litterers. Litterers, and it's a hard word to say. I don't even know how to spell it exactly. Litterers or not. And this is amount of litter. Okay, and so those are our 2 categories. Okay, and let's put the numbers in here, and we know that there are 17 who dropped when there's no litter and 102 that did not. And there was 28 and 91 and 49 and 71. Okay, and so we've done that. We've defined our variables. We know what we're looking at. The next thing is we're going to state the appropriate hypothesis. And whenever we do a hypothesis test with chi-squared, the null hypothesis is always the name of the test. And then you just write it in context. So the null hypothesis is going to be the amount of litter, and decision to litter or not, decision to drop or not, are, here we go, name of the test, independent, are independent. There is the null hypothesis. The alternative is that the amount of litter and decision to drop are associated or are dependent on each other. Okay, and so the null, keeping track of which is the null and alternative, the null is always the name of the test. And that always helped me figure out how to keep track of which one I was going to try to do. All right, and so we've done that. Now the assumptions, now in order to do a chi-squared test, there's a certain assumption that has to be true. The first one is the data is counts. What I mean by that is that these are like we're counting people. It's not like a measurement, but a count. Like, oh, like imagine you could like make a tally chart. Oh, this one dropped. This one dropped. Oh, this one didn't drop. This one didn't drop. So you're counting objects as opposed to measuring things and having a continuous scale or their counts. We have to have a randomization, so each data point is independent, and the expected counts at least 5, and we're going to talk about that in a bit. If it's less, we're going to combine. And so we know these 2 are good. We do not know this last one yet. We have to figure out our expected counts as we go forward. So now we're going to do the calculation for that. The first thing we're going to do is we're going to do the expected values. And we need to know how to do this with and without our calculator. So here's our table. And we know there were 17 people here that did it, and there was 102 people. And so in total, I know there was 119 subjects in the no litter. And we also know that there was 28 here, and 91 here, and 49, and 71. And so there's 119 here and 120 here. When I add this way, there's a total of 94 litterers and 264 who did not litter at all. So this is 358. And so to find the expected value, well, in this particular case, I know there's 119 out of 358 in total. So proportionally, there was divided by 358. So I know there was 33% that dealt with no litter. And if 94 people of all of them had dropped it, then that should be the proportion if these should be proportional. So I'm going to multiply that 33% times 94. And so I should, if all things are equal, there should be 31.2. This is the expected value that I would expect. And so I find the proportion, multiply by this. And so the easy way to think about it is I take my total. So if I want to find this particular one, I take my total 119 times this total divided by that. So 119 times 94 divided by the grand total. So you take your row total, your column total divided by the grand total. And again, that'll be 31.2. If I want to do this one, I go 119 times 264 divided by 358. And when I do that, I get 87.8 and so on. And so the question that I'm really asking myself is, with random variation as part of what I realize happens, are these numbers close enough to say they're the same, or are they so far apart that you say, oh, there's an effect of having no trash there, so there's going to be some litterers. It's going to affect it. So we're asking to see, are these expected values close enough to the actual values to see if it is indeed there's a relationship or not a relationship. And so these values here, when I do this one, is 88.5 because it's 120, and this one here will be 31.5, and so on. So here are my expected values. Now, our calculator will do this, and I'll show you how to do it in just a second. So we want to know, basically, is this expected value close enough to the observed? And so in order to actually calculate this chi-squared statistic, we are going to do the sum of the observed minus the expected squared, dividing it by the expected. And we're going to do it for each of them. So the first cell would be 17 minus 31.2 squared plus 31.2. Plus, then I would go to this one. I would go 102 minus 87.8 squared divided by 87.8, and so on. All these values here is how I calculate this chi-squared statistic with this particular formula here. For degrees of freedom is basically going to take the rows minus 1. So in this case, there are 2 rows, so 2 minus 1. And I'm going to multiply it by the columns. Oh, sorry, there's 3, my rows and columns. There's 3 rows, 1, 2, 3, 3 rows, and then it's the columns minus 1, which is 2 columns minus 1, which will be 2 times 1. So the degrees of freedom in this case is 2. And so I just want to talk about the expected values. My assumptions, expected counts are at least 5. And these are clearly at least 5. If they're not 5, we have to combine categories. So looking at our checklist, we can do the expected values now with and without a calculator. Well, I haven't shown you with the calculator yet. The chi-squared, we add these all up. And then degrees of freedom and our p-value. So now we're going to go to our calculator. And the first thing we're going to do is I'm going to go to my matrix, which is second matrix. And I'm going to edit A matrix. And I'm going to make it a 3 rows by 2 columns. Make sure it matches. And then I'm just typing the actual values. Got 17 102, 28, 91, 49, and 71. Enter. Okay, so that is matrix A. Now I'm going to go to Stat, Tests, and I'm going to go to Chi-Squared Test. Not Chi-Squared Goff Test, but Chi-Squared Test, C. Hit Enter. The observed values are in matrix A. I type that in. The expected values, it's going to compute these green values all by itself, and then I can calculate it. And so now I know the degrees of freedom is 2. I can say that my p-value, the p-value is equal to 0.00001 if I counted my decimals correctly. 35, so approximately 0. And my chi-squared value, if I would add up all these 6 cells, it would end up being 22.4. And if I go to my matrix, to B matrix, if I look at it, it will put all my expected values into the matrix here. And you can see there's a little arrow there, so if I scroll to the right, I can see them. So it will do, the calculator will do all the expected values for you. If you want to see, I believe it will graph it for you. I'll talk about the chi-squared graph. We'll draw it. So the chi-squared graph, they are all similar in the sense. They all are always one-tailed. And so the chi-squared graph kind of goes like this idea. The higher the degree of freedom, the more stretched out it becomes, similar to that. This is degrees of freedom 2, so it's actually quite steep and over here. And so here is my critical, here is my chi-squared was 22.4. And this area is 0.00001, the p-value. Now I was told the chi-squared critical was 9.1. Well, 9.1 would be here. The chi-squared critical to find the critical region. And so clearly my chi-squared value is inside the critical region, so I will reject the null hypothesis because I could say my chi-squared is inside the critical region, or the p-value is less than alpha. So first part, reject or don't reject. Second part, give a reason. And then, so we claim sufficient evidence to say amount of litter and litterers are dependent. So meaning the more litter, the more likely people will throw trash down on the ground. And so this is our chi-squared independence. The calculator will do a lot of the work, and there's lots of steps that you should do with and without your calculator or know how to do them.